Okay, so we've learned about ionic compounds. Most compounds, however, are not ionic. Most compounds are ones in which atoms don't transfer electrons, but they share electrons. And these compounds are called covalent compounds. Now later on in chapters 9 and 10, we're going to study covalent compounds excessively. All we got to worry about today are looking at some of the different simple types of covalent compounds, learning how to identify them, learning how to relate names and formulas. Unlike the ionic compounds, in which the identity of the cation and the anion dictate what the formula is going to be, they dictate how many cations you need for how many anions, it's very difficult to predict all of the covalent compounds, and so we're not going to worry too much about generating the formulas. What we are going to worry about is, here's the name, what's the formula, here's the formula, what's the name. Now the first kind of covalent compound we're going to study are the simple called binary covalents. These are ones in which you have two different types of atom. The way you name them is very simple. You name the two atoms and each one has a prefix. Now when I say name of atom, it's not quite that simple. You put the atoms in a very specific order. The first atom is the one that is further to the left on the periodic table. If both of them are in the same group, then the first atom listed is the one lower down, and you just use the atom name for that first atom. But then the second atom, in other words the one that's more to the right, or if they're in the same group, the one that is higher up, you use the ide form of the name for that second atom. So you wouldn't say oxygen, you'd say oxide. You wouldn't say chlorine, you'd say chloride. Now when we say prefix, we're talking about, for each atom you have there, the prefix refers to how many of that type of atom there are, and there's a special code that we use for that. 1 is mono, 2 is di, 3 is tri, 4 is tetra, and then after that we get into the familiar series where 5 is penta, 6 is hexa, 7 hepta, 8 is octa, 9 is nona, 10 is deca, and so on. Now those 2 pages, while they're not necessarily confusing or somewhat clunky, it's much easier to just do some examples. So P4S6, look at that formula. It contains 4 phosphorus atoms and 6 sulfur atoms. First thing we got to decide is which order are we going to list the phosphorus and the sulfur. It doesn't necessarily relate to the formula there, although in this case, as you'll see, it does. Phosphorus is to the left of sulfur on the periodic table. There's phosphorus, there's sulfur, so therefore phosphorus will be atom 1, sulfur will be atom 2. Phosphorus we use its straight name, sulfur we turn to the ide form, so therefore this is some kind of phosphorus sulfide. Now there are quite a few phosphorus sulfides. Which one is this one? Well, this is the one in which we have 4 phosphorus atoms and 6 sulfur atoms. 4 is tetra, 6 is hexa, so we just pop those in front as the prefixes to get tetraphosphorus hexasulfide. Let's do another example. Br2Cl7 contains 2 bromine atoms, 7 chlorine atoms. On the periodic table, these are in the same group, and bromine is below chlorine. So bromine is going to be the first atom, chlorine will be the second atom. As bromine is the first atom, we use its name. As chlorine is the second atom, we turn it into its ide form. So this is some kind of bromine chloride. Again, we look at which bromine chloride it is. It's the one that's got 2 bromines, 7 chlorine atoms, 2 is di, 7 is hepta, and so this is dibromine heptachloride. Of course, it wouldn't be chemistry if it was that easy, so there are always some exceptions to the naming. First exception is one that just really goes for convenience in naming. There's no huge sense to it other than it's just how we do things. First one is, if there's only one of the first atom, then you omit the mono just from the first atom. If you got one of the second atom, you put the mono in, but if only one of the first atom, then you don't put the mono in, except sometimes. So thus CO2 is carbon dioxide, not monocarbon dioxide. And then if the prefix combined with the atom name puts two vowels in an awkward fashion, you omit the vowel on the prefix. This is something that is very, very, very inconsistently applied. I'm not going to try and trick you on it, but I do just want you to appreciate that. For example, CO, it should be monocarbon monoxide. Okay, well, of course, we already said the monocarbon being at the start just becomes carbon, and then instead of monoxide, there's really nothing wrong with saying monoxide, except when you write it, it looks like monoxide, and so we leave out the O that's at the end of the prefix, so it just becomes the familiar carbon monoxide. However, you are going to see people who even leave off the mono as well there, so just carbon oxide you would read as CO. If people are, of course, applying the rules even semi-correctly. And then, of course, as you'll see as we go through the class, if there's going to be one atom that messes it up, it's going to be the Aggie atom, hydrogen. All right, hydrogen is, of course, normally stuck off all the way on the left of the periodic table, but the way that we actually do the naming of it, we consider hydrogen to be above nitrogen. It's not above nitrogen on the table, that's just the way that the sequence goes. So for example, the very familiar H2O should be called dihydrogen monoxide, because we say that hydrogen is to the left of oxygen, right? Conversely, however, BH3 is boron trihydride, because here hydrogen is right of the boron. Okay. One thing to point out to you here, and we're going to see this many, many times through, is that as you look at naming of compounds, a lot of these naming sequences came up in the 1920s, the patterns, the conventions for naming them. But there's a lot of molecules, a lot of compounds that were extremely familiar before that and had non-systematic names, or so-called trivial names. So of course you're never going to find somebody who calls H2O dihydrogen monoxide, because its trivial name, its much more familiar name, is water. And there's actually a very funny little sequence of things online where people claim to have gone out and done surveys and so forth, asking for this dangerous chemical dihydrogen monoxide to be banned, because, for example, dihydrogen monoxide, this horrible chemical, is a fundamental component of acid rain. It's responsible for 100% of deaths by drowning. It is found in 100% of people who have cancer, and so on and so on and so on. And the urban legend is that a lot of people vote to ban that very dangerous chemical, water.